Hello, and here we are for the second video on forces in motion for the year 13 bit of the A-level mechanics course of the second year. So let's get straight to it and have a look at some worked examples. So we're just following on exactly from where we got to last time. So have a look at these examples now, just 1, 2, 3 questions to have a go at. Write them down if you've not got a worksheet in front of you. Press pause now, attempt them, and then press play to see what the actual solutions are. Righty-ho. Without waiting any longer, let's have a look together at question 1. Question 1, we have a triangle ABC, which has been partially labelled. So ABC is a right angle as shown, ACB is 30 degrees as shown. However, AC equaling 10 hasn't been drawn on, so we can add this to it like so. We need to find AB and AC. So what we could do, if we don't remember from last time and a bit of chapter 4, we could just use SOHCAHTOA from GCSE, like so. So like I said, the hypotenuse is 10. That's hypotenuse because it's opposite to the right angle. So to find AB, which is this side here, oops, wrong colour. To find AB, that's involving the opposite side because it's opposite to the 30-degree angle. So I'm going to highlight the O because I want to find the opposite. What side do I know already? I know the hypotenuse, which is 10. So we're going to pick whichever triangle gives us most information. This triangle here has 2 things coloured in, more than the other 2, so we're going to use this SO triangle for sine of the angle. So for AB, sine 30 is the opposite, which is AB, divided by the hypotenuse, which is 10. And therefore, AB equals 10 sine 30. So it's actually probably better and easier to see if we leave it in this form. So if we wanted to find instead CB, now CB is the adjacent side. So we're no longer interested in the opposite, we want to find now the adjacent. So if we were to highlight on A for adjacent, we'd see that the cosine triangle gives us most information. So to find BC, we'd be using CA. So in other words, C means cos of the angle, so cos 30 would be the adjacent side, BC, again divided by the hypotenuse, which is 10. Therefore, BC would be 10 cos 30. Now, in fairness, this question does ask us what AB and BC actually are, so we can evaluate these to 3 significant figures. But the main thing I want to focus on, which was what was mentioned last time, is if we know the hypotenuse and we have an angle, then the side opposite to the angle is always going to be the hypotenuse sine of the angle, and the adjacent side will always be the hypotenuse multiplied by cosine of the angle. So that's the most important thing to remember. But anyway, to answer the question as it is asked, AB is 10 cosine 30. If you've forgotten your exact trig ratios, don't worry, this is what the calculator's for. That gives us 5 root 3. In fact, we can leave it in 5 root 3 form, why not? And 10 sine 30. That's just going to give us exactly 5, because sine 30 is 1/2. So that's that question completed. So let's have a look now for warm-up for question 2. Question 2 here, we've got a particle P of mass m that's being pushed up a smooth slope by a force F as shown. F acts parallel to the slope, so it's going upwards relative to the slope, parallel to the slope, and it's inclined at an angle of theta to the horizontal. For the partially completed force diagram below, first off we need to work out angle A in terms of theta. So angle A is just this bit here. So we can deduce that this triangle from this corner to P to the bottom, that's going to be a right-angled triangle. That's 90, that's theta. Angles in a triangle obviously sum to 180. And so angle A plus theta plus 90 needs to add up to 180. So therefore angle A is 180 minus 90 minus theta, which gives us 90 minus theta. Then, for part B, we need to deduce angle B in terms of theta. Now, the way I've drawn this here is I've drawn a component of a weight, where the weight is mg, acting parallel to the normal reaction force. And so this is acting perpendicular to the slope. And so this angle here, A and B, add together to make a right angle as shown. So we can say that A plus B equal this right angle, so A plus B equals 90 degrees. But we know that A is 90 minus theta. So 90 minus theta plus B equals 90 degrees. We can then just subtract the 90 from both sides. So minus theta plus B equals 0. A bit of rearrangement, it's not too hard. We can hopefully convince ourselves that B is angle theta. And this is going to be particularly useful in this chapter. So B and theta are one and the same. In part C, based off this, in terms of mg and theta, resolve the weight of a particle into components perpendicular and parallel to the slope. So perpendicular is going downwards like so, and parallel is going downwards according to this arrow. So we just need to add into these boxes here what these components are. So from warm-up question 1, hopefully we've remembered that the component going opposite to the angle, if we know the hypotenuse, is going to be the hypotenuse multiplied by sine of the angle, which is theta. You could say sine B, but we want B in terms of theta. B is theta, so that's mg sine theta. And the component going along is mg cos theta, hypotenuse multiplied by cos of the angle. So we can generalize this result here to resolve forces nice and easily when forces are acting on a slope. So the general idea is this. If we've got a particle on a slope inclined at an angle theta to the horizontal, then if this is theta, then the angle that the vertical makes with the line which is perpendicular to the slope is also theta. So this angle and that angle will always be one and the same. Therefore, we can resolve the component of the weight. The component of the weight which is perpendicular to the slope acting downwards is mg cosine theta, and the component of the weight acting downwards and parallel to the slope is mg multiplied by sine theta. Finally, warm-up question 3. We have this particle P acted on by forces as shown. The particle is in equilibrium, so the sum of the forces in any direction is equal to 0. We now need to calculate the magnitudes of the forces F1 and F2. So first of all, let's think about forces left and right. So the sum of the forces in the left and right directions will be equal to 0. Another way of saying this is the total of the forces acting to the right will be equal to the total of the sizes of the forces going to the left. So the forces acting to the left, the only one here is just F1. So therefore F1 will be equal to the forces going to the right. And there's only going to be one force, which is from this 2 Newton force, which we can resolve along this direction, and we can also resolve vertically too. like I said before in warm-ups question 1 and 2, the component opposite to the angle is the hypotenuse, the magnitude of the force in this case, which is 2, sine of the angle, and the magnitude of the force for component going along is the hypotenuse, cosine of the angle. So F1 must be equal and opposite to 2 cosine 30. And that's actually all we need to do. So F1 is simply 2 cos 30, so we can evaluate that. So what is 2 cos 30? Well, 2 cosine 30, that gives us root 3. So if we wanted it in a decimal, we could round and say it's about 1.73 newtons. And now for F2, we need to consider forces going up and down. So considering in the vertical direction, the sum of all forces vertically will equal 0. In other words, forces up, E will equal forces going down. Going upwards, we've got this force of 5. We've also got acting upwards this component of this 2 Newton force, which is 2 sine 30. Those are the total of the forces acting upwards. The only force acting downwards is F2. So therefore F2 is just 5 plus 2 sine 30. Let's see what that gives us. So that gives us exactly 6. So F2 is 6. F1 is 1.73 newtons. Let's move on now using this idea of resolving forces perpendicular and parallel to a slope and just have a look at some more worked examples together before you try some of these questions on your own. So let's dive straight into some more examples. So, worked examples of objects on inclined planes. First off, we've got a block of mass 20 kilograms sliding down a smooth slope angled at 15 degrees to the horizontal. First off, draw a force diagram to show all the forces acting on the block. Fairly standard. So draw horizontal. This is angled at 15 degrees to the horizontal, so I'm just going to draw this in like so. This angle is 15 degrees. So that's where this 15 comes from. It's a block of mass 20 kilograms. We can model this if you want to as a particle. That's what I'm going to choose to do. So obviously it will have a weight. So if its mass is 20, that means its weight will be 20g. There will also be components to consider of this weight which we might want to add in. I would suggest we do that now in fact. So going downwards, perpendicular to the slope, and then parallel as well. So like we mentioned before, if this is 15, this angle here will be 15 too. The component which goes opposite to the angle will be 20g hypotenuse multiplied by sine of the angle. And the component going this direction, the adjacent component if you like, is 20g cosine of this angle. This force diagram isn't yet complete because there will be a normal reaction force which will always act perpendicularly, will act normal to the plane. So we do a arrow like so, going upwards, and we can call this N for the normal reaction. Now I'm convinced here I've not left myself enough space. I do this all too often, which is silly. You'd think I'd learn, but I never seem to. So I'm going to call this N, which is the normal reaction force. I could, I suppose, if I wanted to, say that because the particle isn't going to float off a slope or fall through it, this normal reaction force must be counterbalanced exactly by the forces acting away from it. So this will be equal and opposite to this 20g cos 15 force. 20g cos 15 component of a weight, I should probably say. And what do we know? We've killed two birds with one stone, because B actually asks us to calculate the magnitude of the normal reaction of this slope on the block, which essentially we've done now. So for B, the normal reaction is 20g cos 15, and so we can fairly easily calculate this. So 20 multiplied by g, we must remember is 9.8, multiplied by cosine of 15, that gives us this awkward looking surd. To get it into a decimal, press the SAD button. We've got 189 newtons. I'll just say that's to three significant figures. Next, for part C, find the acceleration of the block. And so what we can do here is we can consider forces acting parallel to the slope. By the way, if this idea confuses you, just to remind you of the general idea from before, we'll always have this. So this is what I'm using to decompose a force into two components like so. So forces acting parallel to the slope. There's only one force acting parallel to the slope, which is 20g sine theta. So if we apply the good old F equals ma, going down the slope, then the force going down is just 20g sine theta with nothing counteracting it because it's a smooth slope. Pay attention. So 20g sine 15 will equal the mass of a block, which is 20, multiplied by its acceleration. Therefore, if we just rearrange this, so A will be 20g sine 15 divided by 20, so essentially these 20s cancel, and just bear in mind, as you can see here, the 20s cancelled, which was the mass, so the acceleration is once again independent of the mass, just like we saw in free fall for year 12. The acceleration on a smooth surface is also independent of the mass too. So A is just g sine 15, which is, well, let's see. So 9.8 multiplied by sine 15 gives us approximately 2.54 meters per second squared. Let's check out another example. This time we've got a particle of mass m pushed up a smooth slope by a force of magnitude 5g newtons acting at an angle of 60 degrees to the slope, causing the particle to accelerate up the slope at 0.5 meters per second squared. Show that the mass of this particle is 5g over 1 plus g kilograms. So again, because it's acting up a slope, we might want to resolve this perpendicular to the slope and parallel to the slope too. So let's use this to our advantage in terms of resolving the weight both perpendicular and parallel to the slope. So this force diagram isn't quite complete yet, but we'll get there. Its mass is m, so its weight is just mg. In fact, I'll do that in just a normal black colour. So then we've got here going down perpendicular to the slope, and also we'll have a component going parallel to the slope. So opposite to the slope, this component is mg sine of this angle, which is always the same as this angle, which we can see as 30. So I'll just add in, that's going to be 30 degrees as well. This one is always the same as that one. And going down the slope perpendicular to it, we'll have mg cos 30. So what else do we need to label here? Well, there will be a normal reaction force, so I'm just going to add this in. Normal reaction always goes perpendicularly away from the slope, so it's always at right angles. I'll call that n. Do we need to work that out? Do we not need to? We'll just leave that there for now. We might be able to get away with not actually doing this. And then this 5g force as well is actually at an angle, so we can use the same idea to resolve this. We can resolve it going perpendicular and parallel to the slope, just as we did with the weight. So going perpendicular to the slope, we're going to have a component like this, and going parallel to the slope, we're going to be having a component going like this. So using the same idea, we can say the component opposite to the angle is the hypotenuse, which is 5g, multiplied by the sine of this angle, so that's going to be 5g sine 60. And the component acting parallel to the slope will be 5g cos 60. So I'm just going to do an arrow here so it's not getting too crowded. Now we're told this particle is accelerating up the slope, so there's no acceleration in any other direction, just simply up the slope. So we can just consider forces acting parallel to the slope. So we just need to decide on a positive direction. Let's have going up the slope as positive, so up the slope we'll take as being positive. We can now apply F equals ma. So the force is going up the slope, well there's only one, it's the component of this 5g pushing force going up the slope, which is 5g cos 60. So pushing up the slope, parallel to the slope, is 5g cos 60. And that's the only one, whereas acting down the slope is the component of the weight of the particle acting downwards, which is mg sine 30. That's the overall resultant force parallel to the slope, and that'll equal mass multiplied by the acceleration. Now we're told the acceleration of this particle is 0.5, so we can just substitute this in for a. So that's going to be 0.5 multiplied by the mass. So next, we can work out what these bits are here. So 5g cos 60, so what's that going to be? Let's just see. So 5 multiplied by, oh we don't need it in terms of, we need it to leave it in terms of g, don't we? We say yes. So what's 5 times cos 60, I wonder? 5 times cos 60, that's going to give us 5 over 2, which is 2.5 if you prefer. So we're going to have 2.5. Then what I want to do here is to get all the terms in m onto the other side of the equation. So if I add mg sine 30 to the other side, I'm going to get 0.5m plus whatever mg sine 30 is in terms of g. By the way, this here, 5 cos 60 is 2.5, so it's only 2.5g. Apologies, just almost missing that out. So mg sine 30, well what's sine 30, I wonder? You should hopefully know that sine 30 is a half. So this is going to be 0.5m here, then plus m times g times 1/2. So that's going to be 1/2 mg. You can see here there's fractions or decimals in my case, so if I just get rid of these by multiplying both sides by 2, that might be a nice way of neating it all up. Double 2.5g gives us 5g, double half the mass gives us the mass, and then double this gives us mg. We can now factorise out of this m, so 5g equals m, brackets 1 plus g. Therefore, if we divide both sides of this relation by 1 plus g, we can isolate to find what the mass is. So therefore, the mass is going to be 5g divided by 1 plus g, which is what we wanted to show all along. And we're done and dusted because that was a question. We wanted to show that the mass of particle was that, and we have done. So our job here is complete. Let's have a look at one more, then it's time for you folks to try some on your own. Question 3, have a particle of mass 2 kilograms moving up a smooth slope and is being acted on by a force of 4 newtons that acts parallel to the slope as being shown. The slope is inclined at an angle alpha to the horizontal, where tan alpha is 3/4. I'm going to mention this in a moment. Work out the acceleration of the particle. So again, just to remind us, how do we resolve a weight which is perpendicular and parallel to a slope? We can do this. So let's do that here. But in our case, theta is actually this alpha. So just add on the information we need. Perpendicular and parallel to the slope. So this is going to be alpha as well. Going opposite to this angle will be the mass, which we're told is 2 kilograms. Because the mass is 2 kilograms, the weight will be 2g. So the component of this opposite to this angle alpha is just going to be 2g sine alpha, and the component acting perpendicular to the slope will be 2g cosine alpha. Whoops, made a slip. As well as that, it's fair to say there will always be a normal reaction force acting perpendicular and upwards from the slope. I'm going to label this n, like so. Now, we don't need to work out n again here, because all we need to work out is the acceleration of the particle, and the acceleration will be going either up or down the slope. Okay? There's no reason to be thinking that it's going to jump off a slope. No force is going to push it away from the slope. The normal reaction just supports an object, it never makes it fly off. And in the same way, the gravity doesn't suck you towards the centre of the Earth and makes you fall through the floor. It's not quite that strong, so it's going to stay on the slope. So the acceleration is either going to go up or down the slope. So my inclination here is to pick a positive direction. So I'm going to take going up the slope as being the positive direction. You could take going down to be positive. It really is up to you, as long as you're consistent with the labelling. So up as positive. Now tan alpha is 3/4. There's a few ways we could work out alpha. I'm going to show you the best way after. It's tempting here, and this will work in this case, to think, well, if tan alpha is 3/4, I can simply just do, well, alpha will be tan minus 1 of 3/4. So if we work this one out here, tan minus 1 of 3/4. We get a fairly ugly looking angle here. It's about 36.86989 and so on. So 36.869 and so on. But if you leave this in this exact form and then do sine and cosine of this angle, then sine alpha is sine 36.869 and so on and so on. But if I leave it in this exact form, which the calculator's given me, and just press sine of the answer, weirdly I get 3/5 exactly. Whereas cosine will be cosine of this 36.869 dot 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 and so on. So again, if I work that out, sine minus 1 to get it back again, and do cosine of that, I get 4/5. Isn't that weird? Well, actually it's not. I'm going to give you a more sophisticated way of thinking about this, and this will be very useful when it comes to doing trigonometry for year 13. Examiners often, not always, but often give you an angle in terms of tan, or sometimes a different trig relationship. So why would they do this? Well, what you need to remember here is what tan is. Okay, so tan of an angle is a ratio of the opposite side to the adjacent. And what I'm going to show you here is a better, more sophisticated way of thinking about this. So bear with me as I just go from this little detour. So the ratio of the opposite to the adjacent is for every 3 it's going up, we're going along by 4. So we can sketch this triangle, thinking of it in terms of right angle trig. So I'll just move this down here. Okay, whoops. So I'm going to label that alpha. So opposite 3, adjacent 4. So the opposite and adjacent are in this relationship. We can now use Pythagoras to work out the hypotenuse. So hypotenuse will be the square root of 3 squared plus 4 squared, the square root of 25, which is 5, but hopefully you should remember, this should jog your memory, that 3, 4, 5, it's going to make a 3, 4, 5 Pythagorean triple. So using this idea now, we could easily see what sine is without having to use the calculator at all. So this idea of drawing it out is very powerful. Remember, sine, so, is ratio of the opposite to the hypotenuse. Opposite 3 divided by 5, 3/5. Likewise, cosine is a ratio of the adjacent to the hypotenuse, which is 4/5, like we had doing it the long-winded way. That was worth a mention in its own right. I'll mention that as we go through the teaching this year again, but it was worth dropping in. Back to the question at hand, the acceleration of this particle. So we took up to be positive, so going up the slope is this 4 Newton force. Going in the negative direction, going down the slope, is this component of a weight 2g sine alpha. I now know what sine alpha is though, so that's 2g sine alpha is 3/5, so sine alpha, you can just substitute that in. And by the way, I should have said we're using F equals ma. So the resultant force going up is that. So that will equal the mass of a particle, which is 2, multiplied by the acceleration of a particle. So therefore the acceleration will be 4 minus 2 times 3/5 g, so minus 6/5 of a g, divided by 2. Let's work that out. So 4 minus 6/5 times g, which is 9.8. Divide that by 2. What do I get? We'll get minus 3.88. So minus 3.88 meters per second squared. So what does this mean if it's a negative acceleration? It means acceleration is acting in the opposite direction to what we took as being positive. So rather accelerating up the slope, it's going to be accelerating down the slope. So I could say in brackets, it's accelerating at a rate of 3.88 meters per second squared down the slope. That's the implication of this minus here. It's going down the slope rather than up. That's all I've got to say on these really. It's now over to you to try this idea and get fluent and confident. So if you move on to these exercises now, page 98 and 99 on exercise 5b in the Stats and Mechanics book, try them all, check your answers regularly, as I'll always say, and if you're still stuck, ask a friend who you work with, or ask me either in class, on email, or in the comments section. Thanks very much for watching this video, even if it's just been a couple of minutes. Do please subscribe, it's very nice when you do, and keep safe. I'll see you all very soon, I should hope. Bye for now.